Obviously, the pandemic has kind of caused us a little bit of a scheduling problem this year, and so I'm asking you all to do a little bit of extra work sometime between the last week or so of the part of the year before winter break and at the end of winter break. Whether or not you're going to do that over winter break or you're going to do that over the next 10 days or so, I don't really care. I just want people to have the opportunity to get a start as soon as you can. I really think this will free us up maybe a week or so in the schedule. And as you get farther into the school year, you never look back and think, man, I sure wish we had spent more time on some topic. You always want more time to get ready as the spring goes on, especially as you start getting into some of the tougher applications. So I'm really trying to pick some topics here that are either slight extensions of things we've done before, relatively simple, maybe something that's even a review of a previous topic, all right? The first topic we're going to take a look at is referred to as Riemann sums. Riemann sums are actually named after a German mathematician whose name I think was actually Georg Riemann, but I believe he went by Bernard Riemann. Lived in the mid-1800s, I think 1820s to about the 1860s, died reasonably young. I believe he was a student of Gauss, and as you go deeper and deeper into different math courses, Gauss is going to continue to be unbelievably important. Anyway, Riemann actually had some really deep discoveries that had huge impacts on the study of calculus. And the one I'm getting ready to show you really is relatively simple, but it's kind of the basis of the idea of the definite integral. And so even though it's very simple, it's a really important idea. So let's take a look at this problem here. We're asked to find an estimate for the definite integral of x squared plus 1. Now you'll see some additional notation here. You've got this kind of S shape here with a 1 and a 4, and you've got a dx. We haven't worked with the definite integral notation a whole lot other than earlier in the year, and I'm not sure we use this notation very much, if ever. So there'll be a few things there we need to kind of look at. But basically we're trying to estimate a definite integral using something called Riemann sums. Okay, so here's the visual. Okay, remember that a definite integral is really just an area under a curve. Technically the area under the curve down to the x-axis, or I suppose if your curve is below the x-axis, it would be the area up to the x-axis. Okay, so the visual we have here is, this is a parabola. By the way, we are working with the function y equals x squared plus 1. We're going to more fully understand the idea of that dx moving forward. It's not really going to affect anything you're doing in these problems, although it will always be there. So our function is y equals x squared plus 1, which is basically a parabola. And I'm not so worried about having a graph that's drawn really well to scale. I'm interested in having a graph where I can label key points. And this is very much like what we did with the trapezoidal rule estimations as well. Okay, so this notation here is the notation for an integral. It's an elongated S, which is very similar to the kind of Greek S we have with the sigma symbol, okay? There is a connection between this symbol and the sigma, okay? And there's a reason that they both have a shape that's related to an S. Again, that'll become a little bit more clear as we continue to learn more about definite integrals. But anyway, our function is y equals x squared plus 1. This is telling me that I want to find the definite integral between x values of 1 and 4. Okay, so specifically I'm looking at the graph here at 1 and then over here at 4. All right. Here's how Riemann sum works. We've already done the trapezoidal rule, and we found the areas of trapezoids under a curve. The Riemann sum, instead of using trapezoids, actually uses, wait for it, rectangles, okay? And rectangles are much easier to find the area of than trapezoids, which makes Riemann sums very simple to find. Now, you may be thinking, now, wait a second, we're going to estimate the area under a curve with rectangles. Isn't that kind of ridiculous? And the answer is, on the surface, yes, it seems like it would be kind of stupid in comparison to trapezoids, okay? But there's a reason that it's not as ridiculous as it sounds on the surface. So let me show you. So this is going to work pretty much like the trapezoidal rule. You would probably be given something like, n equals 3 rectangles, something like that, okay? You'd be given the number of rectangles you're going to break it up into.
And so you take your region, you break it up into that many regions. And so we'll have a rectangle that goes from 1 to 2, we'll have a rectangle that goes from 2 to 3, and we'll have a rectangle that goes from 3 to 4. I guess I should extend my graph up a little bit there. From 3 to 4, maybe something kind of like that. Okay, and I don't really need this part of the graph because I'm not finding the area under that part of the curve or under that part of the curve. Okay, now, there are several different types of Riemann sums. There's a left Riemann sum, there's a right Riemann sum, and there's a midpoint Riemann sum, are probably the three most traditionally used. Okay, so let's look at what a left Riemann sum would look like. A left Riemann sum just says that you're using the leftmost point in each interval for the height of your rectangle. Okay, so that means I'd be picking the point at 1 and making that the height of my rectangle. So we can see this rectangle is pretty significantly below the curve. Okay, and then I'm picking the point at the far left here in this interval, and I'm making a rectangle. And then for this interval, I'm picking the point on the far left, and I'm using that point, okay? And you can see just the way this curve is bent. This doesn't apply to every single curve, but for this particular curve, because the curve is increasing, all of these left-hand sums are going to underestimate the actual integral, okay? And again, in some cases, it looks like they underestimate by pretty much, okay? So on the surface, you look at this and you think, it's not really a very good estimate. Okay, now let's go ahead and find this. Remember, on the AP exam, they're going to want to see your calculations. So even if you have a calculator program that does Riemann sums or something like that, make sure that they can actually see what you have. I suggest listing the functional values at each of these particular points. So if you go back to the original function, 1 squared plus 1 would be 2, 2 squared plus 1 would be equal to 5, 3 squared plus 1 would be equal to 10, and those are the heights that you need. And basically just show your sum. So each of these rectangles in this particular graph have a width of 1. So you have a base times a height of 1, times a height of 2 for that first rectangle. You have a base of 1 times a height of 5 for that second rectangle. And you have a base of 1 times a height of 10 for the last one. And let's see, 2 plus 5 plus 10 looks like an estimate of 17 for that definite integral. Okay, and by the way, that's an underestimate. Because the curve is increasing, and so it's going above each of those rectangles, okay? Now, you look at that, you go, well, that's not a very good estimate, is it? Well, no. But there are other estimates as well, okay? There's also a right hand, or a right Riemann sum, okay? So let me show you the right Riemann sum. Same thing. We're going to do it with n equals 3 rectangles, okay? And for a right Riemann sum, you pick a point on the right side of the interval to create your rectangle. So, for example, in this interval, the point on the far right would be that point right there. Our rectangle would kind of poke up out of this particular curve. For this interval here, I pick the point on the right. That's going to serve as my height of my rectangle. And then finally over here, I'm going to pick the point on the far right. That'll be my rectangle, okay? This time, because the curve is increasing and I'm picking points on the right, the rectangles are going to be above the curve, which means this area is going to be bigger. It's going to be an overestimate, okay? So anyway, same kind of thing. You need to show the calculations for the areas of each of your rectangles. By the way, 4 squared plus 1 would be 17 for that one. So we have a rectangle here that's a 1 by 5. Okay, so we have a 1 by 5. We have a 1 by 10. And then we have a 1 by 17. Okay, and so 10 plus 17 is 27. 27 plus 5, I believe, is 32. Okay, so by the way, this does narrow things down a little bit. We had an underestimate of 17. We had an overestimate of 32. So the actual definite integral should be somewhere between 17 and 32. Now, that's still a very large range, but you know, it's not terrible. All right, so there is also what's referred to as a midpoint Riemann sum. And for most curves, the midpoint Riemann sum is probably going to be the best, okay? The midpoint Riemann sum is going to pick a point exactly halfway between the two coordinates. And, well, let's take a look at how that shape is going to change. So for a midpoint Riemann sum, okay, so we've got points here again at 2 and 5 and 10 and 17. For a midpoint Riemann sum, you're going to be picking a point halfway between the two x-coordinates. That would be at 1.5, whatever f of 1.5 is. And by the way, in this function, that's going to be a little bit tougher to do off the top of your head. Okay, so you're going to pick a point there at 1.5, and that point there is going to be f of 1.5. You're going to pick a point halfway between 2 and 3, that's at 2.5, so you're going to figure out what f of 2.5 is. Okay, and you're going to make a rectangle there. And then you're going to pick a point halfway between 3 and 4. That, of course, would be 3.5 in this particular case. And you're going to use whatever the functional value of 3.5 is. Okay. Now, I'm going to run a table here because those numbers are a little bit messier. You know, maybe if they gave you rectangles with a width of 2 or something like that, it might be pretty easy to do that. But anyway, it's a good case for using the graphing calculator table here. So I'm going to start my table at 1.5, and I'll have it count by ones. Okay, so f of 1.5, and by the way, to show work, you can actually say the area of this rectangle is going to be 1 by whatever f of 1.5 is. That's actually a good way to show your work, okay, where your answers are coming from. Plus, this rectangle is a width of 1, it has a height of f of 2.5, and then this final rectangle has a width of 1, and it's got a height that is f of 3.5. And we can just run those numbers then. So f of 1.5 is 3.25. F of 2.5 is 7.25. And f of 3.5 is about 13.25, okay? And if we add those two things up, 3.25 plus 7.25 plus 13.25 is 23.75, okay? And by the way, remember, we had predictions before of 17 and 32, and notice this is going to be really close to the value that was estimated basically by averaging the left and the right sums. So it's not a linear curve, so it's not exactly the average of the two, but it's pretty close, okay? So notice, by the way, the good thing about the midpoint Riemann sum, if you have a curve that's only increasing or only decreasing, notice part of the rectangle is a little bit above the curve, part of the rectangle is a little below the curve. And so you kind of have this underestimate here that gets offset by an overestimate here. It's not perfect. You know, these are not exactly the same shape. These are not exactly the same shape. You can see this is a little bit bigger than that is, and so on. So the underestimate is a little bit farther off than the overestimate, that sort of thing. But it's still pretty good, okay? If you have a good picture, the midpoint Riemann sum can be very simple to calculate. If you don't make a good drawing and you don't plot the points for your graph, you don't find those functional values or use a table that they give you, these problems can be relatively difficult, okay? Now, the final thing here, you're looking at this and you're saying, well, you know, why is this, what's good about this in any sense? You know, why would you use this instead of using a trapezoid? Wouldn't a trapezoid follow the curve better? And the answer is, for a couple of rectangles, yes. But that's not really the big idea here. The big idea here is, as you create more rectangles, you're going to get better and better and better estimates, okay? So if I pick, you know, maybe rectangles that are a half a unit wide, for example, maybe using a left-hand sum, okay? My rectangles might be kind of under the curve, maybe a little bit like this, and you can see that those are matching the curve much better than the rectangles were matching the curve before, okay? If you want to have even smaller rectangles, you know, make each rectangle 1/10 of a unit wide or something like that, and, you know, suddenly you can start to get something that follows the curve pretty incredibly well. And as you have more and more and more of those rectangles, the area is going to get closer and closer to the actual area, which, by the way, means that as the number of rectangles approaches infinity, or you could say as the width of the individual rectangles approaches 0, the overall sum of those rectangles is going to approach the actual definite integral, okay? And that is exactly what we are looking for in these problems, okay? So that's the idea. That's a Riemann sum,
okay? It is much easier to find the area of a rectangle than it is to find the area of a trapezoid. It's a much simpler formula, and that's going to lead us to simpler formulas to work with when we're finding actual definite integrals as opposed to just doing estimations. By the way, it's very easy to program a calculator to find Riemann sums, and a calculator can have very many very thin rectangles and give you very, very accurate answers very easily. So very simple, I think, to see how that could potentially be pretty useful. Okay. By the way, I want to mention two other things. On the AP exam, they're most likely going to ask you for left sums, right sums, or probably a little more than half the time midpoint sums. Okay, but be ready for any of those three. Forrester actually talks about something called upper sums and lower sums, which are also a thing. Okay, the upper sum or the lower sum means when you pick your interval, you're either picking the lowest value in that interval or you're picking the upper value in that interval. Okay. The interesting thing about that, and Forrester uses this term, he'll use like a big U and a 3 for the upper sum. For the problem that we just did, if the function is only increasing or only decreasing, then your left-hand sum or your right-hand sum is going to match up with either an upper or a lower sum. In other words, if I do an upper sum, breaking this up into 3 rectangles, the upper value in the interval would be on the far right, and so we get a rectangle there. The upper value in this interval would be on the far right, and we get a rectangle there. The upper value on this interval will be on the far right. And so for an increasing function, the upper sum and the right sum are both going to be the same thing. Okay? For an increasing function, if I wanted to find a lower sum, okay, go back here, do a lower sum. The lower sum, you're picking the lowest value in each interval. So the lowest value is going to be on the left. The lowest value in this interval is going to be on the left. And the lowest value on this interval is going to be on the left. And so, again, the lower sum here and the left sum would be the same thing. Okay? On the surface, you think, well, then why do they even have these? Well, technically, there's no rule that the function has to only increase or decrease. Okay? So I think there's a homework problem where you've got like a sine function or something like that, and the function's doing this kind of thing, and it's possible that your lower sum might be on the left-hand side over here, and by the time you get over here, your lower sum might be on the right-hand side. Meanwhile, if you had an interval, right here, for example, if you had an upper sum, the upper point would actually be at that vertex point there, which could be somewhere else inside the interval. It doesn't have to be at one of the endpoints. It doesn't have to be at the midpoint. It's just the highest point in that interval. So if the function changes direction somewhere in the interval, it might be something that's not one of the endpoints or the midpoint. So just some things to think about. Again, I don't think they really use the upper and lower midpoint on the AP exam that much. But by the way, the actual definite integral will be in between the upper sum and the lower sum. And so if you find that limit that the upper sum and lower sum are approaching, they're basically going to squeeze that actual sum in the middle there, and that's where your actual definite integral comes from. So you basically have an upper bound coming from the upper Riemann sum, and you have a lower bound coming from the lower Riemann sum, and somewhere in between those two values you're going to find the actual value. Okay, so anyway, pretty simple concept, much easier than using the trapezoidal rule. Same overall concept, but you just need to be aware that they could ask for right, left, or they could ask you for the midpoint sum. Also, be careful, sometimes they give you a table of values. You may not have rectangles that are all the same width. Don't make up values, use the value on the values that they give you on the table. And also be really careful to pay attention to the number of intervals they want you to use, because that's going to tell you how you're spacing things out. That's going to tell you where your midpoints are, those types of things. So there are lots of little details to pay attention to, but in the grand scheme of things, you're getting points on the AP exam for finding areas of rectangles, okay? And when it comes down to it, you can't beat that. So hopefully that overview gets you to the point where you're pretty comfortable working with problems involving Riemann sums.